All right, let's dive right into this explainer. Today, we're going to uncover an invisible biochemical engine that literally powers all life on Earth, the nitrogen cycle. Now, we usually think of oxygen as the most important element for survival, right? Or maybe carbon as the ultimate building block of life. But there is this unsung hero working behind the scenes. Nitrogen is absolutely essential for creating the amino acids in our bodies, our DNA, and even the chlorophyll that plants use to soak up the sun's energy. Without it, the living world just grinds to a complete halt.
But here is the crazy thing. We are basically starving in a sea of plenty. 78% of the air you and I are breathing right now is pure nitrogen gas. It's by far the largest component of our atmosphere. But here's the catch. Almost none of the plants or animals on Earth can actually use it in this gaseous form. It's swirling all around us, constantly filling our lungs, and yet it is completely out of reach biologically. So, that brings us to a massive paradox. If nitrogen is literally everywhere, why is it so incredibly hard to use? Well, despite its abundance, atmospheric nitrogen is completely locked up. The nitrogen atoms are bonded together so tightly that plants just cannot break them apart to absorb them. It creates this severe scarcity of usable nitrogen in most natural ecosystems. Life needs nitrogen desperately, but the atmosphere's massive stockpile is locked inside an impenetrable vault. To figure out how nature solves this problem, we're going to trace the path of the nitrogen atom. We'll start with the paradox of plenty, move into nature's microscopic relay race, dive into the marine nitrogen cycle, look at how we eventually started hacking the natural balance, and finally confront the toxic cascade effect. Okay, Section 1, the paradox of plenty. Unlocking the atmosphere. Let's look at how the Earth historically bridged the massive gap between the useless nitrogen floating up in the sky and the hungry life down on the ground. The crucial point here is that nitrogen must be fixed. It has to be transformed from that stubborn, inert gas into a biologically usable form. Historically, this heavy lifting was handled by two main forces. First, high-energy lightning strikes. The intense heat of a lightning bolt can actually rip nitrogen molecules apart, fixing between 5 and 10 billion kilograms of nitrogen every single year. That's huge. But actually, the vast majority of fixation is done quietly, by highly specialized microscopic life known as diazotrophs. Which leads us to Section 2, nature's microscopic relay race, the soil engine. Let's dig into the dirt and see how this all builds into an invisible relay race driven by bacteria. You can really think of the whole cycle as microbes passing the nitrogen baton through 4 distinct steps, so plants and animals can actually use it. First, fixation pulls it from the air. Then, when plants and animals create waste or die, microbes perform aminification, turning organic matter back into ammonia. Next up is nitrification, which converts that ammonia into nitrates, which plants just love to drink up. And finally, denitrification completes the loop, sending the nitrogen right back up into the atmosphere as a gas. So meet our tiny pit crew. These microscopic workers are incredibly specialized. For example, rhizobium bacteria actually live right inside the root nodules of legumes, like peas and alfalfa. It's a really beautiful symbiotic relationship where they trade the fixed nitrogen they produce for the plant's carbohydrates. Meanwhile, Nitrosomonas and Pseudomonas handle the middle and end of the cycle. It's basically a highly coordinated biological assembly line.
But there is a catch. This relay race has to maintain absolute perfect balance. Why? Because if ammonia builds up in the soil during this process, it actually becomes highly toxic to the very plants trying to grow. This requires our nitrifying bacteria to rapidly step in and convert that dangerous ammonia into safe, usable nitrates and nitrates. The entire ecosystem relies on this incredible chemical tightrope walk just to survive. Now let's scale this up globally with Section 3, the deep blue cycle, nitrogen in the ocean. Because this isn't just happening in the dirt. Let's see how this plays out beneath the waves. The ocean essentially runs on 2 types of nitrogen. Marine life relies heavily on regenerated nitrogen. That's nitrogen constantly getting recycled near the sunlit surface by phytoplankton and bacteria. But it's the new nitrogen, entering from deep ocean upwelling or fixed by marine cyanobacteria, that truly sets the ocean's total capacity to sustain life. If we just harvest fish from areas relying only on regenerated nitrogen, we end up depleting the whole system. We absolutely need that new nitrogen to keep the marine engine running.
The ocean also features some pretty amazing biological shortcuts. Take the Anammox process, for example.
This is a fascinating trick where marine bacteria convert ammonia and nitrite directly into nitrogen gas and water, entirely skipping several of the steps we see on land. It's an incredibly efficient process, and it accounts for a massive proportion of the nitrogen being returned to the atmosphere from the sea.
This brings us to a major turning point in Section 4, Hacking the Natural Balance, the Human Intervention. For literally millennia, this beautiful biological engine just purred along at a steady pace, balancing everything perfectly. But then, faced with a rapidly growing human population and nutrient-poor soils, we decided to hack the system. We figured out how to completely bypass the microbes. We replaced the slow, natural fixation of the pre-industrial world with massive industrial and agricultural interventions. We planted millions of acres of legumes, we started burning fossil fuels, but the biggest hack of all was yet to come. Enter the Haber-Bosch process. This was an industrial marvel invented in the early 20th century, and it was an absolute game changer. By using extreme temperatures and massive pressures, scientists found a way to forcefully combine nitrogen gas from the air with hydrogen to synthetically produce ammonia. Today, this single industrial process produces about 30% of the world's total fixed nitrogen. We literally changed the carrying capacity of our planet. By utilizing this process to pump out chemical fertilizers, alongside burning fossil fuels, human beings have more than doubled the annual transfer of nitrogen into biologically available forms across the globe. Think about that for a second. We took a fundamental planetary cycle that took millions of years to balance, and in less than a century, we basically threw it into overdrive. Which, unfortunately, leads us straight to our final chapter, Section 5, the toxic cascade effect, breaking the cycle. Doubling a planetary biochemical cycle comes with a really heavy cost. We've created what scientists call a dangerous toxic cascade. Our artificially created reactive nitrogen doesn't just stay neatly tucked away in our farm fields. It escapes. It floods into the atmosphere as nitrous oxide and ammonia, causing smog and acid rain. It washes into our waters as nitrates. We are literally leaking reactive nitrogen everywhere, and it is fundamentally altering the chemistry of our air and water. And when it comes to global warming, you really need to hear this number: 300. Nitrous oxide, which is a direct byproduct of our agricultural fertilizers, is a greenhouse gas nearly 300 times more potent than carbon dioxide at trapping heat in our atmosphere. Plus, it trips all the way up into the stratosphere where it actively destroys the ozone layer. It's a massive issue. Down on the ground, in our waters and lands, all this excess nitrogen basically acts like a dangerous steroid. When fertilizer runoff hits our rivers and oceans, it triggers eutrophication. We get these massive, explosive algal blooms that block out sunlight and suck all the oxygen out of the water, creating huge aquatic dead zones where fish literally suffocate. On land, the extra nitrogen over-fertilizes wild ecosystems, allowing really aggressive, nitrogen-demanding grasses to just choke out naturally diverse plant life. And eventually, this cascade reaches us. Because nitrates are highly soluble, all that agricultural runoff leaches straight down into the groundwater that countless communities rely on for their drinking water. And here's the scary part. Once consumed, those nitrates can react with organic compounds right inside the human stomach to form nitrosamines, which are known cancer-causing agents. The threat to public health is so significant that the World Health Organization sets a strict short-term limit of exactly 50 milligrams of nitrate per liter of drinking water. And let me tell you, keeping our drinking water below this threshold is becoming increasingly difficult and expensive for towns surrounded by modern, intensive agriculture. So we've successfully hacked nature's microscopic relay race. And let's be clear, without the Haber-Bosch process and artificial nitrogen, we simply could not grow enough food to sustain the billions of people living on Earth right now. But here's the ultimate question. Can we rein in this overwhelming nitrogen cascade? Can we figure out how to optimize our fertilizer use, drastically reduce our runoff, and clean up our emissions before this invisible engine completely breaks our ecosystems? It's a huge challenge, but one we absolutely have to face. Thanks for exploring this fascinating invisible engine with me on today's Explainer. See you next time.